Hello everyone, I'm Gengwang, the second author of this paper. Next, let me to present our paper. Nowadays, the coders have compared many executables with linking many libraries, such as OpenSSL, and shipped them to various devices. A year later, Hybrid is discovered, which compromises user privacy. As security researchers, we would like to locate that valuable functions. Here is our problem definition. Given a function for query, we would like to match it in a corpus which is prepared previously. Considering that the executables are binary files, we should match between assembly code. It's not easy since the source code may be compared with different optimization and even obfuscation. Code transformation from optimization and obfuscation is a change 1. The code fragment in the left is compiled without optimization, so there may exist unreachable blocks in the function. What's worse, if it's also obfuscated, here will be more junk blocks. Now it becomes very hard to tell whether these two fragments are similar with each other. To make the comparison viable, we want to eliminate this code that has no side effects and simplify it to a unified form. To do so, data flow analysis is in need. However, there is no variables in assembly code, but only addresses or pointers, so we actually need pointer analysis. That is, we need to link the usages with their corresponding definitions. Here comes the change 2. It's very hard to balance between efficiency and precision. Due to the loop existing in a control flow graph, there's no topological sorting algorithm for the analysis. Hence, you cannot make sure the definition is analyzed before its usages. Here is an example. If we process line by line, the new definition of C in block 4 will invalidate the computation in block 2, which means any fixed path analysis cannot be precise. Iterative analysis is more precise. It maintains a work list which is initialized with the entry of CFG. Each term, a block is popped out for processing, and then its successors are pushed into the list. The question is, the package from block 4 to block 2 invalidates the previous computation, which causes block 2, 3, and 4 are pushed again for recomputation. Due to the use-defined relationship is under building, we can only analyze every line in those blocks. There will be many redundant recomputation. But if we maintain the use-defined relationship on the fly, the overhead on maintained dominating definition will become one major bottleneck of the analysis. In this paper, we target these two challenges. For challenge 2, we design a new algorithm to link each address usage with its dominating definition on the fly, which means we construct defined usage on the fly, and we can also maintain dominating definition in constant time instead of whole square root of n. For challenge 1, we transform the code to canonical form. We will eliminate junk instructions, which has no side effect to the output. We also canonicalize expressions into a unified form. But before we start, let's recap some key concepts. Domination. If any pass from start to a block Bi, must pass a block Bj. We say Bj dominates Bi. For example, block 1 dominates block 4. Dominated frontier. If Bj dominates one parent of Bi, but does not strictly dominate Bi, then Bi is a dominated frontier of Bj. For example, block 4 is a dominated frontier of block 2 and of block 3. Dominating definition. If a usage has only one reachable definition, then this definition is also a dominating definition for that usage. For example, the definition of A in block 1 is a dominating definition for the usage in block 4. However, the definition of B in block 1, 2, or 3 is a dominating definition for the usage in block 4. A package points from a block to its ancestor. Any block pointed by a package is a backward block, and the other blocks are forward blocks. The analysis should be performed in such an order that any definitions incoming to a block are processed previously, so that the recomputation can be reduced as many as possible. But for a directed cyclic control flow graph, there is no such an order. How to distribute the process order? When to do the recomputation? Can the recomputation be done sparsely? This question we will answer in the rest of this paper. For forward block, we observe that there exists such an order that can make sure any definitions reaching a forward block can be analyzed previously. We can traverse the CFG in reverse pulse order, processed line by line. Several components are maintained. E traces the dominating definitions. C maintains the unallocated SSA version number. DU is the set of defined use edges. We maintain these components on the fly. Several components are maintained. E traces the dominating definitions. C maintains the unallocated SSA version number. DU is a set of defined use edges. We can maintain dominating definition in constant time. Here is an example. The new SSA version number will be fetched from the table C to variable X, and then the table E will be updated with the new SSA number. The second and third line are processed in the same way. Since the block 1 dominates the others, so no special propagation is required, but block 2 is different. Except the entry block, each block should inherit the table E from its dominator. Block 2 will inherit from block 1. Then the same update is performed. Since the dominator frontier is a joint point, so a phi branch is inserted to the dominator frontier. In this way, definition is propagated along with the iterative dominator frontier chain. But how to process backward block? To make sure the recomputation can be scaled correctly, before we talk about this, we first give a definition for backward reachable graph, give a CFG and a backward block. All the blocks that can reach that block only through its back edges, and all the edges on such passes constitutes the backward reachable graph. For example, the backward reachable graph of block A is shown in the graph. We observe that a backward block belongs to the adept chain of any block in its backward reachable graph. Remember that when we process the forward block, the definition can be propagated through the adept chain. So we can take block A as a forward block by converting the back edges into forward ones. Then we can process its backward reachable graph just as what we have done to a forward block. After that, we can recompute the expressions that use the variables of the incoming new definitions. Therefore, we can update sparsely along the UD chain. A nested loop can be processed in the similar way. Another benefit for processing the backward reachable graph is that there will be less invalidation events. Now we can introduce our re-optimization framework. There are two phases, canonicalization and elimination. In canonicalization, two more components are maintained. D stores the definition expressions, and A maps address expressions into recount variables. The canonicalization process the abstract syntax tree from leaves to the root. It substitutes every pointers with the corresponding definitions. Then many reduced rulers are applied for canonicalizing the expressions. After process, the code fragment should be like this. Any constant expressions have been evaluated. The expression will be simplified and the copy operation will be reduced. As for the elimination, the max swap algorithm is applied to remove these unused and unreachable instructions. The return value, the function parameters, and the global variables are marked as used initially. After that, the usage information will be propagated along with the defined use chain. After all, any instructions that have not been marked as used will be eliminated. All in all, the query code fragment and the reparator code fragment will be re-optimized into a unified form. Then, any comparison model can be used to evaluate the similarity. In this paper, we show the state-of-the-art assembly-to-vector model. Finally, we evaluate our method. We collect 6 real-world programs from the open source. There are around 20,000 functions in total. We compare these functions by GCC with different optimization levels O0, O2, and O3. We also obfuscate these functions with these obfuscation methods provided by obfuscator LLVM. So each function will be compiled into 6 different versions. Then the corpus size should be around 120,000. In this paper, we choose top K accuracy for the evaluation. That means each function and the compilation configuration will be compared with every function in other configuration. Now let's see the performance against the optimization. Firstly, the O0 vs O3 case is demonstrated. This case may represent the biggest difference between two different optimization configurations. The figure shows that our method improves the top 1 accuracy in this case by 22% on average, and the top 5 accuracy by 25% on average. Though a symbol-to-vector claims that it could capture semantic information, the re-optimization still has to promote the performance. As for the case O2 vs O3, these two models are comparable in the top K accuracy. The reason why re-optimization has little influence in this case is probably because the optimization options enabled only by O3 are mostly about code structure, such as local optimization, which is not related to our method. Although in O2 vs O3 case, our method gives an ordinary performance in top K accuracy, but ROC in Figure B says our method will slightly improve the performance after a very small false positive, which is less than 2%. In Figure A, the improvement is very significant. Also, the good performance indicates that our method has very little negative effect on similarity. As for the case against obfuscation, our method performs stably against the obfuscation substitution, the bogus control flow, and the pointer-based obfuscation, but has a bad performance against the control flow flatten. As for control flow flatten, which deal with structure instead of data, our method has no special effect on it. The evaluation of our method against the substitution has a few more false positives is because compilers' early optimization will reform a few obfuscation rulers so that the rulers becomes too complex to be matched. In all, Our method shows resilience to the obfuscation that based on data dependency. Next, we demonstrate the efficiency of our method by comparing to SDA, which is the most efficient approach that supports both point and reachability analysis. We mainly compare the overhead on dominating definition, since it takes up around 80% of the SSA transforming, as shown in the table. The experiment results show that our method costs only 8 seconds to maintain the information over 20,000 functions, while SDA needs 127 seconds. The copies of table E between blocks may be the implicit cost of our method. The clone column in the table shows that this extra overhead is very small and has approximately linear relationship with the update of method. Totally, our method has a 15 times speed up on average for maintaining the information about the dominating definition. In conclude, in this paper, we believe the optimization and obfuscation would affect the code feature by equivalence substitution and by removing or inserting jump code blocks. For alleviate that effects, a precise pointer analysis is required for canonicalizing and for eliminating those jump code. To address these challenges, we designed a new algorithm to transform SSA code on the fly. We've shown that the bottleneck of the transformation can be computed in constant time, and it's also easy to scale between efficiency and accuracy by controlling the loops of sparse update. We also present a reoptimization framework based on our new algorithm. We use this framework to reoptimize the lifted binary code precisely and efficiently. Of course, our method is not without limitations. Firstly, our method only addresses this code transformation that's based on data flow, which means our method will have little effect on other transformations, such as the structure transformation flatten. And secondly, the canonicalization applied by our method is limited by reduction ruler matching mechanism, which means our method will not be purely precise. It's because the reduction problem is actually NP-hard. And last, our method is inner function analysis, which means any obfuscation or transformation across the function boundary would invalidate our method. That's all. Thanks for your attention.